Welcome to Statics and Mechanics of Materials. Today we'll be discussing the concept of force. I have drawn materials from three different books. There are the books from Hibbeler, Bedford, and Beer and Johnston. So what is the ultimate goal in mechanics of materials? What are we trying to accomplish when we're looking at structures? What we're trying to do is to design optimal structures so that when they're subject to forces, that they're robust during their service life. Here's an example of an electric transmission tower. This transmission tower is stabilized by cables, and the support cables do exert forces on the tower and at their points of connection. Um, what are the loads acting on this transmission tower? It could be the weight of the transmission tower itself, could be the winds pushing on the tower and potentially bending the tower. And so what is reacting those loads are these cables. What are forces? So a force transmits load, and a force is a vector and has a line of action. Um, and typically, the units of force will be Newton in SI units. Um, you could have external or internal forces. External forces could be such as drag, could be frictional forces, it could be lift. Internal forces are those that are getting reacted internally to the material. You also have body versus surface forces. A body force could be such as gravity. Surface forces are those that are acting on the surface of the material. We do have three types of forces. We have frictional force, uh, spring force, normal force. We also have non-contact forces. No forces need to be applied in direct contact. And so those are like gravitational force, electrical force, and magnetic force. And so these are the two kinds of forces you could have, the ones that are contact and the ones that are non-contact. So if we look here, we have a force system, and a force system is said to be concurrent if the lines of action of these forces intersect a point. If you have forces that are in parallel, so say you have FB, the vector FB, and FD, in this case, FB and FD are considered to be parallel. While FA, FB, and FC, these three forces which have a direction and magnitude, they intersect at a given point, and so these are called concurrent forces. Coplanar forces would be all these four forces. They're all acting and lying on the same plane. So all these forces are coplanar in this example. Gravitational force can be represented by a vector. Typically, if I'm trying to figure out where this force is acting, I can apply it to the centroid of the object. The magnitude at sea level is related to the mass m times the gravity, or times g, which is acceleration due to gravity at sea level, which can vary depending upon where you are. What you could be in Mars or a different terrain, different planet, and g will be different. Therefore, your weight will change. While mass is the same, doesn't matter where you are in the universe. Springs can also carry force. As an example here, I have a spring that's unstretched. And the spring, when it's displaced an amount S, if the spring has a spring constant K, then the force will be force equals K, the spring constant, times S. So the force required to displace that spring from this configuration to this configuration is K times S. Force equals K times S. The magnitude of the equal and opposite forces exerted on two objects connected by a linear spring is basically spring constant times the length of the spring minus the length of the unstretched length. Okay, so in this previous example, if this is a length L, not the initial spring length, and this is a final spring length, that's L minus L naught, which is S. And so here you have the same formula, F equals K times S, which is a difference in the lengths between the stretched and unstretched configurations. The forces acting on A and B due to a spring connecting these two pins, the forces will be equal and opposite, but they will be acting the same line of action. And so the force is a vector again, and their magnitudes will be the same, but they will be acting in opposite directions. Here's more examples of unstretched spring. So when I have an unstretched spring, if I were to stretch it and then connect it between two pins, then there will be a force that's in tension. But if I have a spring and I connect it to two supports that are shorter than the length L naught, then I'm compressing the spring. So two different scenarios could occur. Contact forces. When two planes here, for example, are in contact. So you have two surfaces in contact from each object. The orange object is different from the blue object. And this object come into contact, and what goes on is that there's a force exerted on the right surface due to this contact. This force F, which is a vector, can be resolved into two components. The normal component to that surface and then the tangential component to that surface. Typically this F here, which is tangent to the surface, will be due to frictional forces, while the normal force N is acting perpendicular and normal to that surface. If only the normal force N is shown, then we have neglected the frictional forces. Here's an example of two curved bodies contacting each other. In this case, the dashed line indicates the plane tangent to the surface that's at the point of contact. So if this is the dashed line that's tangent to the location where the two surfaces contact each other, then I can draw a normal force. So I'll remove this object here in orange, and I'll replace it with a normal force N and a frictional force F. This normal force N is perpendicular to the dashed line, which was tangent to the point of contact. While force F, small capital F, that force is along the line of action of that dashed line and is also considered a frictional force. Here's what goes on when you have a contact force. The contacting objects will exert equal and opposite forces to each other. So if I look at the force acting on A, that same force is acting on B, but in the opposite direction. And then when I look at the left-hand side, I have a force N applied and a F frictional force applied tangent to that surface. Well, N is normal to the surface. If I look at the other side, object blue, and I remove object blue and replace it by forces, I'll have opposite N, a force opposite N, and then a frictional force F going downwards. So again, it will be equal but opposite forces. Ropes and cables are typically used extensively, and they have similar behaviors to spring. The important thing to understand is that cable connecting A and B, for example, will have again forces exerted on A and B that are equal and opposite in the same magnitude but opposite directions and parallel to each other. So the line of action for F bold here is the same line of action of F bold here. Here's an example of ropes and cables application. So now you have a crane here attached to a box. Um, so here the tension load is T bold, but then from the crane perspective is T bold but negative because it's the opposite direction, same magnitude, however. Here's an example of a pulley, and the pulleys are significantly used in a lot of applications. Uh, if you look at a pulley, typically the tension force on a rope or cable on one side will be equal to the in magnitude as the tension in the cable on the other side of the pulley. So the tension magnitudes are the same. The directions typically will be along the line of action, which is parallel and is along the cable. So again, the tension force T1 will be along the line of action, which is along the cable length. And so that's what you see here. So it's a good assumption to assume that the tension force is the same in both ends in terms of magnitude. Let's look at what's going on here, and this is more of a review because we kind of done this before. I want to better understand through a few examples how we can resolve force F. So I have a force F acting, and I have a Cartesian coordinate system X and Y with an angle theta in between. And I want to know what the component of F is on the X and the Y axis. To do so, what I'm going to do, I'm going to transmit this force, but I'm going to translate it a little bit so it's in the origin here at this point. The force F can be decomposed into the X and Y direction. So I can take this F, use the direction cosines, projected to this X axis, and what I'll get is a vector Fx, which is equal to F cosine theta. So that force F is cosine theta, F cosine theta. And then I can project F onto the Y axis, and that one is going to be F sine theta, or F times cosine of 90 minus theta. This angle here is 90 minus theta. So I can multiply F times the cosine of this angle to project it into this dashed line, and that will be the F times cosine 90 minus theta, which is the same thing as F times sine of theta. As you can see, the vector F in this direction, in the X direction, is acting in a negative sense compared to the X axis that should have a negative sign. And then F here is pointed so that when I project it into the Y axis, also pointed into the opposite direction as Y. And so here are your answers for this example. Another example could be a force F applied in this manner, but I can again translate it to this location and then apply the rule of direction cosines. So if I project F onto the x-axis, that is F times cosine theta to get the component of that vector along the x-axis. It's pointed positive, so I should expect a positive F cosine theta value for Fx. For Fy, when I project this onto the y-axis, I get the F sine of theta. And it's acting the opposite direction as the y-axis. So it should be a negative sign, and that's exactly what we see. So we could continue with this approach. We have now another example of a force F, and I want to know the components of this force along the x and y axis. You can see here that that this is a bracket in this case, and it has an angle beta along this bracket. Um, it's a fairly straightforward problem. we could see that this angle here is beta minus theta. Okay, why is that? If this angle is beta, this angle here is 180 minus beta. Okay, if that's 180 minus beta, since this is a triangle and this angle is theta, this angle here must be beta minus theta. So all I have to do now is to take this vector f and project it onto the y-axis. That's simply f cosine beta minus theta, but in a negative sense because it's acting in the opposite direction as the y-axis. So fy again is the minus f cosine beta minus theta. Fx will be f. Again, I will now project that onto the x-axis, so that will be along this direction perpendicular to the y-axis, so that will be f sine of beta minus theta. Let's construct a force vector for this example. So I have a cable that exerts a tension of 2 kilonewtons on the fixed bracket at A. And so I want to write an expression for this vector, for this tension vector, T, bold. And so what is the strategy we want to use? So I know the magnitude of this tension force, T, is 2 kilonewtons. So if I want to know how an expression for this vector, what I really need to know is the vector that goes from A to B. And so if I know the coordinates of A, I know the coordinates of B, I can construct a vector that points from A to B and then make it a unit vector. And once I get it to a unit vector, I can multiply by 2 kilonewtons to then get the components of the vector for this particular tension force. So how do we do that? We can simplify the coordinates of point A, find the coordinates of point B, and then if you have those, you can quickly calculate this vector RAB from point A to point B. The coordinates of point A can be found very easily by looking at the geometry. So along the x-axis, this is 1.2 meters. Along the z-axis 0.3, and along the y-axis there's no change for point A. So therefore, these are your coordinates. For B, the coordinates can be found very simply. It lies on the yz plane, so it has no x component, so that's 0. And then for the y-axis is 0.5 meters on the right, to the right of the origin along the y-axis. And then it's also elevated by 0.4 meters in the z direction. So now I can quickly subtract the coordinates of B and A. So 0 minus 1.2, 0.5 minus 0, and then 0.4 minus 0.3 will give me a vector that points in that direction. It's not a unit vector though, but we can simply calculate that that vector here by following the procedure discussed. This minus that, this minus that, this minus that, and that'll give you this numerator. And then I have to find the magnitude of this vector and divide it by that magnitude. So that will give me now a unit vector. That unit vector multiplied by the force of 2 kilonewtons will give me the expression for that tension force acting along A, B cable.